Okay, so I guess it's bigger. Yeah, so yesterday what we did was we were looking at another kind of a problem in base nets, which is called the inference problem, where you're given this query. So you want to find the probability that some random variable q takes a value small q, given the values of some other random variables. So these are the evidence random variables. And the base net has a couple of other variables as well. So that is what we call as the hidden variables. So those are noted by Z1 to Zn. Okay, and the objective now is to compute this probability from the base net. So the issue is you don't have all this probability is not readily available. What you have is some conditional probabilities from the base net. Now, how do you use that to compute these probabilities? Okay, so that's the inference problem, and more generally that comes up in a lot of these machine learning algorithms. So most machine learning models can be represented with a base net, and the inference is a very important problem there. Okay, and so one way to do this kind of evaluation we saw was to enumerate all the values of the hidden random variables, because what you have is a way to compute this joint probability over the entire random variables in your network, because the base net structure gives you a way to do that. So one way to compute this query is to enumerate all the values of the hidden random variables. So that gives a huge number of terms, and so it's not very viable in that sense. So can you do something smarter is what the question was. And the idea was to you make use of this this joint probability computation from the network, but do something smarter in terms of these summations. So maybe group some terms together and do the summation sooner or something of that sort. So that's the idea that we're getting to. Okay, and to do that, what we did was we defined the notion of factors. So those were actually some intermediate tables in your base net, and we were looking at the join operation. So if you look at these kind of computations where you have summations and products, so basically it's you need to be able to do some summations and some products. Okay, so the join operation is basically the product operation. Okay, and it takes two factors. So factors were actually some kind of tables that you have in your network. So some examples of factors were these kind of probability tables. So sometimes these entries of the tables may sum to 1. That is, for example, in this case p of x comma y. So this is actually a joint distribution over x and y. And if you sum up all the entries of this table, all these 4 entries, that has to sum to 1. So assuming that x and y are binary valued. But whereas, something like this, p of x equal to x and y. So this is where you fix the value of x to small x. And so there are 2 entries here. These 2, if you sum up the table, if you sum up the entries, it will not sum to 1. So more specifically, if you sum up p of x and the values of y, right? So this is what your table is going to have. This is going to just sum to p of x. Okay, so it will not sum to 1. So it's not necessary that all factors sum to 1. But these are some tables, and these are like the building blocks. Okay, and you will do some operations on these to to get your query, to evaluate your query. Okay, so this is what we saw yesterday, and we started looking at this join operation. So where if you, for this example, like RTL, so this was a chain-based network. So it was a causal chain, and if you wanted to join these 2 tables, P of R and this was P of T given R. So you could join these 2 tables. What that means is you have a new table with all these columns. So here there's a column for R, and in this other table, there's a column for R and T. So the new table that you get, that's a factor, that's also a factor. So what you're going to get will have all the entries of both these tables, all the columns of both these tables. So you have R and T. So R comes twice. So that just comes once here in the new joint table, this one. And each entry here you're going to get is a product of the corresponding entries from both these tables. Okay, so that's what we saw as a join. It's just a simple multiplication of the entries of each of the tables. And again, we saw, a join of P of, this resulting factor, which we called as P of RT, right? So, so in this case, this was P of RT, and we merged P of L given T to get another factor, right? So that had that this was a new factor, the resulting factor with 8 entries. So there's a column for R, there's a column for T, and there's also a column for L. Okay, so this is what we did, and what where we stopped last class was we were seeing whether the resulting factor is also going to be, the values here, are they going to be probabilities or not? Okay, so what I told you was, yeah, you would like them to be probabilities, but it's not always guaranteed that they are probabilities. And an example I gave you was this kind of a network. So A, B, I mean, there's this, there's a connection from A to B, and from the parents of C are both A and B. Okay, so for this kind of a network, if you do a join of these two tables, P of A and P of C given AB, so this one and this one, so not put a circle. So this P of A and P of C given AB. If you do a join of these two tables, what you're going to get is some factor. So we saw how to write the factor in terms of, again, it's trying to mimic this conditional probability representation, but need not always be. Okay, so here what we had was, in the left part of this bar, I mean, I don't know what this symbol is called, but anyway, you have A and C, because A appears in two factors, one's on the left hand side and one's on the right hand side. So here you put it on the left, and then you have C, because it comes only on the left hand side, and so the resulting factor, it comes up on the left, and given B, so B comes up only in the right hand side of a factor, so you put it in the right hand side. Okay, so this is the factor that you get. Now, whether this factor is the probability of AC given B, that's the question. And what we saw is this is not the case here. Okay, so for this network representation, if you wanted P of AC given B, how you would need to do is more generally with chain rule. So P of A given B times P of C given AB. Okay. Now the thing is, P of A given B, this is not necessarily equal to P of A in this graph, because A and B can have some dependence relationships. So in this case, this factor, it's just an intermediate value computed, and it's not necessarily equal to P of AC given B. Okay, but one thing is, if you join all the factors which have A, so in this case, if you join P of A, P of B given A, and P of C given AB, okay, so those are the factors where A arises. So if you join all these factors, this is going to be a valid probability distribution. So this is exactly P of A, B, C for this network, right? So so if you join, so the underlying thing I want to convey is, if you join all the factors where a particular random variable appears, the resulting factor is going to be a probability table. Okay, the values are probabilities, to be more precise. Okay, but if you just join any two tables, it need not be the values that you get need not be probabilities. Okay, so I hope this point is clear to you all. So what I suggest is, maybe I'll just give you some exercise, as a homework. Just try this out. Okay, so I'll just give you this network. So something like this: A, B, D, maybe something like this, C and E. Okay, so this is a network that's there, and the tables are specifically P of A, and here you have P of B given A, you have P of C given B, and here you have P of D given BE. Okay, so what I want you to see is, if I merge, so one thing is, if I join P of B given A and P of D given BE. Okay. Right, so these are two factors, this one and this one. If I'm going to do a join, what is the result I get? Is that going to be, so is that going to be the values that you have in the resulting table, are those going to be probabilities, right? So the way to do that is you need to understand the underlying semantics of the base net, and you need to use deseparation to see whether particular independencies hold or not. So let me just write a little bit here. The new factor that you're going to get in this case is B comes in both sides. So what happens is B will come on this side, and then you have B, the factor will have BD given A, E. Okay, so what you need to do is you need to check whether this is going to be equal to probability of BD given AE. Okay, so that is something that I want you to try. And also, also verify that, if I multiply all these factors, so this is one operation. The other join I want you to try is if you have P of B given A, P of B given BE, and what's the other one? P of C given B, right? So what do I get here? What's the new factor? Is that going to correspond to a particular conditional probability or not? Okay, so these are some things I want you to try as homework. This is going to come for the exam. Okay, so I'm just telling you now itself. All right. So I just want to pause for a minute and just ask: are there any questions on the join operation? Is the idea clear?
Yes, ma'am.
It's clear? Okay. It's a simple thing, right? It's just the multiplication of the tables. That's it. The only thing is that you might not find in many places the explanations about whether these correspond to probabilities or not. So typically people just say that it corresponds to probabilities, but I want you to understand that it's not always the case. You need to do something more to verify that these are really probabilities. Okay, so that's something I just want you to take away. All right, so this is with the join operation. Now let's go to the next operation. So the second operation here is operation 2. So that is called eliminate. Okay, so it actually corresponds to sums. So we had so remember this whole idea, right? So we were grouping terms together. So that was the join operation where you multiplied the tables. And then there is the summation here. Okay, there's the summation which comes up. So eliminate is just a summation. Okay, so eliminate is just sum. It's just a summation operation. But the purpose is you want to remove a random variable from a factor. So the idea is to remove a random variable from a factor. Okay. So let's again take this example, right? So we had this P of RT. Okay. Now from this network, if you want to, so from this table, this is the new factor that you have, P of RT given MT, or P of RT, that's it. And if you want to, eliminate T from here, right? I want a new factor which only contains R, right? So how will I do that? Or maybe let's just say we want to eliminate R because we started off with P of R and P of T given R. So let's say I want to eliminate R from this table. Okay, I want a new factor which just has T. Okay, so how would I do that? So let me just copy this. Okay, so so this is a factor that I'm starting with, RT and P of RT. Okay, now I want a new table, want a factor with just T. Okay, so how do I do that from this table?
For the same value of T, we sum all the values of R.
Exactly, right? So what you do is you just take plus T and plus T. There are two rows here. So this one and this one. So it's like marginalizing out the R. Okay, so that's just what it is, what eliminate does. So what do you get here? So the value for plus T?
0.24.
0.24, and for minus T?
0.76.
0.76, right? So basically these two values. And the new factor that you get is, so if this is a probability, this is also going to be a probability. Okay, because it's just summing out the values of R. So this is going to give you P of T. Okay, so it's as simple as that. Eliminate just sums out the values corresponding to a particular random variable. So here what we have done is we have eliminated R. So eliminate R from this table gives you this. Okay. Yeah. So now with these two operations, we can do something, right? We can try to compute some query. There's also one more operation which I will slowly get to, but let's just try to do this operation of computing P of L with this. Okay. So let me just copy this chain. So I won't copy the values because that you can look it up. So now what I want to do is this state, I mean, from this chain, I will have P of R, P of T given R, and P of L given T. Okay. Now my query is P of L. Okay. I want to compute the probability of L for all values, like for P of L equal to plus L and P of L equal to minus L. Right. So what I can do is, of course, we have enumeration, but let's not do that. So one thing we can do is we can start by joining these two tables. So we can do a join. So yeah, so what happens is you have initially these are the factors. So these are the initial factors. Okay. Now R and T are the hidden variables. So the hidden variables here are R and T. Sorry, R and T. So what you can do first is do a join of the tables which have R. Okay, so join over R. So what this means is it's a join of P of R and P of T given R. Okay, so this will give you, so this is all tables which have R. So this is going to give you P of RT. Okay, and now what you can do is you can, what can you do here? So now let's take the new factors. The new factors that you are going to have is you can actually get rid of these factors P of R and P of T given R, and you can just use P of RT and P of L given T. So this is the new factor that you computed, P of RT and P of L given T, which was already there initially. You didn't do any operations on it. Okay, so these are the new factors. Now, how can you get P of L from here?
We can eliminate R first.
Yeah, so you can eliminate R. So that is going to give you P of, so eliminate R from P of RT from this factor, right? So that is going to give you what?
P of T and P of L given T.
Yeah, so now your factors are P of T and P of L given T, right? And now what can you do?
Join over T.
Yeah. So the new factors are P of T and L given T. So you just do a join of P of T and P of L given T. So it's understood that it's a join over T. Okay. And so this will give you, what will it give you?
P of joint of L and T.
Joint of L and T. Okay. So this is anyway going to be true always because it's just the chain rule. Okay. And so you have P of TL and now what?
Eliminate T.
Yeah. So eliminate T. Okay, so eliminate T from P of TL. So that will give you whatever you wanted. So P of L. Okay, so this is like a sequence of joins and eliminates. If you do, you can get back a query, a particular query that you're looking for. Okay, so let us see one other possibility, or maybe let's just analyze this first. So here you did a join over R. So initially, let's just see how many entries are there in each of these tables. So in P of R, how many entries would this table have? So all these are binary valued. So how many entries are there in this factor? Two values. What about this one? T given R? Four. right? Yeah, so this has 4 values. And this one,
4.
4.
this also has 4. And now when you joined over P of R and P of T given R, how many entries are there in this one?
4.
This also has 4. Okay, and what else happened? So yeah, so each of these had 4 factors. I mean, so 4 entries in the table. And when you eliminated R, how many were there here in P of T?
2.
2.
This was 2, and this was again 4. P of L given T had 4. What about this one? This join operation?
4.
4 values.
4. And finally, this one?
2.
2.
2. Okay, so you see that by doing this at the max, you're always if you look at all the factors that you got, the size of the factors never exceeded 4. It was always 4, though there are about 8 values here. There are 8 possible configurations. Each of the tables that you got had just 4 values. So there's some benefit in doing these, join, eliminate. Now, I also want to just show you another possibility. So this is one way in which we did a join. So we did join, we did eliminate, we did a join, and then we did eliminate. Okay. Now, another possibility is to, do a join twice and then do an eliminate. Okay. So possibility 2. Right? So the second possibility is first do a join over R. Okay, so that gives you again like so join of P of R. It's the same thing. So P of R and P of T given R. So that gives you back P of RT. Okay. Now what I can do is I can actually do a join with P of L itself. I mean P of L given T. So what I can do is I can now do a join. So the factors I have now, the factors are P of RT and P of L given T. Okay, so I'm ignoring these R and T and these other 2 tables. I'm ignoring these 2, and I'm just going to work with this remaining factors. Now here, what I can do is I can again do a join instead of doing an eliminate. I can do a join over T. Okay, so that is basically join these 2 tables. Okay, so here what will I get? What's going to be the new factor?
Joint of R,
T,
T and L.
R.
So
P of R,
joint of
comma, T, comma, L.
R, T,
T,
comma,
L.
L. Right? So this is a factor, and in this case, it's actually a probability itself. It's going to be the probability of RTL itself. We saw why that is going to be the case yesterday. Yesterday we saw that. So this is the joint, and this has about 8 entries, right? RT and L, all possible values of RT and L. And now you could do an eliminate over R. So eliminate R, so that gives you P of TL. And now what?
Eliminate T.
Eliminate T.
Eliminate T, right? So this will give you P of L. Okay, so here what happens is this is all the same. Like you have 4 entries here. But the only difference is here. This you are creating one joint over all of them. Okay, and this is also 4 entries. This is 2 entries. So so there are different possibilities in which you can compute this query. But the thing is, you want to do it a little smartly. So, by doing some kind of, interleaving of the join and eliminate operations, you can try to make things a bit faster by, overcoming this kind of a huge table creation. Okay, so that's what the algorithm is trying to do. Now, let's try to see what actually is happening here when you try to do these 2 possibilities, right? So what essentially we wanted was P of L. So this was just a sum over T and R. This you had to do. Okay, so P of R, T and L. Okay, so yeah, so I hope this is clear. P of R, T and L. Or maybe let me just write it once explicitly. So P of R, T equals T and L. Okay, so L is given, some value of L is here. Okay, so this is what you wanted to do. And we knew that, this is P of T given R from the network. This is what it was, L given T. and there's again a summation here. And what we did in possibility 2 is we did this operation first. So this gave us P of R T, and we had P of L given T. Okay, so this was actually just a vanilla join. Okay, without doing anything smartly, what we did is this is possibility 2. Okay, because we did this join of these two tables. Okay, and we did a join of this resulting table with L given T, and then finally we did these two summations. So this was actually an eliminate step. So this was an eliminate R, and we did an eliminate T. Okay, so it was not very efficient that way. We didn't make use of any structure. So that was possibility 2. Okay, and whereas if you take the first possibility, what did we do there? So possibility 1. Okay. What happened there? Anybody wants to try? What did we do? We did something with the summations by the way we did a join and eliminate. There was something we tried to make use of.
First, we calculate PT using summation of R, P of R,
Mhm.
and then we have
Yes.
calculated P of L.
We took P of L given T outside the first summation.
Okay, let me just write this down again. So this was the ultimate thing that we had. Okay, and this again boiled down to P of R, P of T given R, and P of L given T. Okay, so tell me what you're saying. I think I heard multiple things, so I just wanted to work this out. So, and was it Advait and Aditya? Or?
Yes, sir.
Yeah. Okay, so maybe who wants to go first? Advait, you want to say what?
Okay, yeah. So we just took P of L given T outside of the first summation over R because it does not have the R variable.
Okay, so we did this.
Yeah.
All right. Yeah. So what happened here? I mean, so we did the summation. So we did this join first, and then we did this eliminate, right? So the summation means we did an eliminate, right? Yeah, that's right. And so this was a new factor, and then we did a join here, and finally this summation. So that gave us an eliminate. Okay. Yeah. So this is what we did. So Aditya, was this what you said, or was it something else?
I said that first we have calculated PT using that summation.
Uh-huh.
Like summation of R using P of R equal to R, T equal to T.
Mm-hmm.
And then we have used that PT to calculate P of L.
Okay, so what you're saying is, I think, a little different. So what you said is, okay, maybe let me just write it
Summation
here
of
for
R.
more space. So you're saying something like this, right? So P of R, P of T given R, and P of L given T. Yeah, so now what are you saying? We did, Aditya, can you say it again?
Like not using summation of T,
Mm-hmm.
can we just calculate first P of T using summation of R, P of R, P of T given R. Then using that P of T, we have calculated summation of T, P of T, P of L given T to calculate P of L.
So this one, this is fine, right? Like what you're saying is this would give you P of RT,
Yes.
right? So after this,
Applying summation of R, P of RT, we can
oh,
calculate.
okay.
So
Okay,
I
so
have
you're
break down
saying
these
this.
things into two parts.
Okay, so that's basically the same thing, right?
Yes.
So same thing is what you're saying. Okay, yeah. So this is actually what we did. Now, there's possibly another way. Okay, you can maybe try to do a join over of these two tables first, right? You can do a join over T, right? So maybe join over T first. Okay, we always did a join over R. Instead of that, you could do a join over T. So that means joining P of T given R and P of L given T. Okay. So this is also another possibility. You do this join, and what will it give you? What's the new factor? Just tell me the factor that you get if
Factor
you do
of
this.
L given R.
L
N comma T given R.
L T given R, right? So this is the new factor that you get, right? And maybe you can, so what you want is an L. So maybe you can eliminate T here, right? Or you could also join with an R next. So there are various combinations possible. So join over R, okay? And finally do an eliminate. So this is also another possibility. So what you're doing essentially is you are taking this summation of T inside. So this possibility is, you're doing P of R comes here itself. But what you're doing is P of T given R and P of L given T. So you're doing this join first and then do this eliminate and then do this join over R and finally an eliminate. So this is also another way to do it. But does it give you any value? That is something you have to see, because here also you're creating a factor. How many entries would be there in this factor?
8.
This will also have 8 entries, right? So there are, yeah, so what I want to hint at is there are these various combinations that are possible. And sometimes, you have to make a choice of what is the best way, what is the sequence of operations you need to do in order to get some query, in order to evaluate some query. Because some orderings are good and some orderings are not good. Okay, so that's one thing. Now, before I formalize the algorithm, the particular algorithm of what we were doing here, I just want to talk of one more operation, which is called the normalize operation. Okay, so this is a third operation, which is called normalize. Operation 3, which is called normalize. But okay, so let me just pause for a minute. Are there any questions on what we just discussed so far and how we put it together to get the query? Any confusions or these possibilities? Or okay, can you all just type whether it's clear or it's not clear, or whether I should go over something once again?
Ma'am, I have one
It's
doubt.
clear? Yes, Aditya. Tell me.
Ma'am, what is the difference between that possibilities? Like there is some sort of complexity difference or calculation difference. Like at the end we are calculating using 8 possible values.
Mm-hmm.
So
Yes.
are there any difference in this?
Yeah, so ultimate quantity that you're calculating is the same. It's just P of n. It's that table that you're trying to calculate. But it's just the way in which you're doing the computation. So because, this is a small example, so you might not see the differences too much. But one thing that I can just tell you here is there are these joints, the 2 joints and 2 eliminates that you have to do. But it's the order in which you change things that sometimes makes a difference. So the complexity wise is what we are bothered about. So the complexity wise, in this case, when you have to do a join over T, the second possibility, there is a slightly larger table. So it's 2 power 3 here. Okay. And more generally, you can end up like if you have larger networks, you can end up because of, if you don't do this ordering properly, there can sometimes be these kind of large tables. Okay, so this is not really large, but what I want to point out is the difference between these possibilities is the size of the factors. Okay, so you want to keep the size of the factors as small as possible. Okay, because once you have a larger factor, now doing this, think of what you did, like when you had to do an eliminate to get this P of Tn. What did you have to do? You had to go over these entries in this larger table. You had to do some summations here, right? So if there were 8 entries here, what you would end up doing is you would have to sum up over maybe more entries, right? You'd have to sum up two entries at each time, and each that you had to do 4 times. Okay, so generally, so if the factor, if each of the tables, if there is any table which is very large, this means that there are some other operations which can get little expensive. Okay, so what you want to do ultimately is you want to avoid that kind of a scenario where you have a very large table. Okay, So the simple enumeration is actually doing this kind of a thing, right? Where so it's just this possibility two is just a very naive way of doing it. It's just expand out all the random variables, all the 2 power n random variables, and do a summation. That's what this is doing. This possibility two. But other possibilities, these other methods are doing something else. They're like doing this grouping essentially. Okay, so the resulting factors are a little smaller. So that's the difference between these two methods. Okay, Aditya, is your question answered or?
Yes.
Okay. Yeah. All right. So, but any other questions or confusions or any thoughts on this? Okay. Okay. So, yeah, so I hope this has been clear. So let me just go to the next operation, which is normalize. So this is an operation. So, okay, so here what we did, an example that we took here was just we wanted to compute P of L. So this is actually we wanted to compute two values here. Okay, so a table containing these two values is what we wanted to do. Now, so there was no evidence here. Okay, so another kind of operation that you do is like, remember we started off by saying you have a query given some evidence. So in that case, so suppose you had a P of L given R equal to plus R. Right? So in this case, you're interested in only this fraction where R equal to plus R. Okay, so if this was the query, then the operations are the same, but it's just that the initial factors you take and there's some more, there's some smaller operations that you do. Okay, so that's what I just want to point out. So here, when you have this, it's again the same network. Okay, so it's the same network. But since the query is L given R equal to plus R, what you do is, so these are the tables that the base net gives you. But your initial factors, since you're only interested in R equal to plus R, what you do is you just pluck out some part of these tables. Okay, so what you do is you don't look at the entire table. So this P of R has a plus R and a minus R. What you do is you just keep the P of plus R. So P of R equal to plus R, you just keep this as a factor. So this is also a factor, right? I mean, a particular instantiation. So it doesn't sum to 1. This table will not sum to 1. So what it will have is this is plus R and this probability, whatever this value is. Okay. So this will not sum to 1, but this is also a factor. So what you do is you just zoom into this part of where, this table P of R, where it has only plus R. You just zoom into that part. So this kind of thing where you pluck out only some part of the table in database management, it's called a project. Okay, so that operation is, it's just a jargon, it's called project. But what you do is you essentially that the initial factor, you only keep the parts which have plus R. So similarly in this table, T given R, what you have is a plus R plus T, plus R minus T, minus R plus T, and a minus R minus T. So what you have in your initial factor is just this part. Okay, and of course these values are there, but you're interested in only this. So that's all that remains. So P of T given R equal to plus R. That's another factor. Okay, and this factor L given T, that you will have everything because there's no dependency on R here, or there's no R coming in any of these paths. So what you will, this factor remains as such. Okay, so these are the new initial factors that you will consider, okay, for solving this query. Now, what is the first operation that you can do, right, to compute this? So basically, there are these hidden quantities. The hidden variable here, what is the hidden variable? Can you tell me?
T.
It's just T. Okay. So what you do is you do a join over the hidden variables and then do an eliminate. Okay. So now there's just one hidden variable T. So you just do a join of the factors which have T. So basically these two. Okay, so your first thing is you do a join of P of t given r equals plus r and P of L given t. Okay, so what is going to happen in the resulting factor?
L comma T given R equal to plus R.
R equal to plus R. Okay, so I will just write this as a factor. So go back and check whether this is going to be a probability. This is going to be, okay, so this is, turns out it's going to be a probability. So LT given R equal to plus R. So now your new factors are going to be, what all do you have? So you'll have P of LT given R equal to plus R. And what else did you have? So these two got merged, right? So these two factors got merged. And what is left is P of R equal to plus R. So these are the new set of factors. Okay. So what you can do now is maybe what did you want? L given R. So to speed things up, you can just eliminate T from this factor. So eliminate T from this one. So that will give you P of, what will it give you?
P of L given R equal to plus R.
Yeah, P of L given R equal to plus R, and you have P of R equal to plus R. Okay, and now what do you do?
We already got what we needed, right?
Okay, so this is what you wanted, yeah, right. So that's what, so you, okay, so in this case, you're actually done here. You didn't need the normalize. So I think I should go for another example. So let me just do that. So, okay, so I think it's the particular, yeah, so maybe the particular set of operations we did is what caused the this thing. Just give me a second, let me just check. Okay, yeah, so this is one possibility, but let's just take another possibility where suppose you did a join on R. Okay, it's not really needed to do it that way, but suppose you did a join over R first. Okay, so right, so what you had was P of R equals plus R and T given R equal to plus R. But suppose you did this, so basically join these two. Sorry. So basically these two, if you join first. Okay, so if you joined these two first, what you would get would be, can you tell me what you get?
P of T
T
and
comma R
R equal to plus
equal
R.
to R plus R.
Yeah, so P of T and R equal to plus R. Okay, and yeah, so now you could, and the other factor that you have is L given T, right? So the other factor that you had was L given T. Okay, so these were the remaining, I mean, the factors, new factors that you had. And now if you did, say, a join of these, okay, so join over these two factors. So let me just write it a bit fast. So this is, if you did a join of these two, what would you get?
Probability of L comma T comma R equal to plus R.
R equal to plus R. And now you could do, and so there's an extra T here, so you could eliminate a T. Okay, so that would give you what?
P of L comma R equal to plus R.
P of L and R equal to plus R. Okay, so now what you wanted was L given R equal to plus R. So this is what we want. We want P of L given R equal to plus R. So how do you get it from this table? Right, so remember this is like plus R minus R. And of course the values of R are just plus R. And these are some entries here. Okay, so from this, if you wanted this quantity, how would you get? If you want P of L given R equal to plus R, how do you
Using
get?
base rule, we can get P
Uh,
of L comma R equal to plus R divided by P of R equal to plus R.
Yeah, so you actually want to do this operation, r equal to plus r divided by probability r equal to plus r, right?
Yes.
And so this operation p of r equal to plus r, from this table, how do you get this?
Eliminate L.
Eliminate L, right? So it's basically a summation of all possible values of L, right? So what you're essentially doing is, you take this table and you kind of scale it. So each entry that you have here, you divide it by the sum. Okay, for example, suppose this value is like zero point 0.1 and 0.6, right? So this value is minus L. So this is possible, right? In this table. Does this table have to sum to 1 or no?
No, because we are taking only one value of R.
Only one value of r. So this doesn't have to sum to 1. So what normalize does on this table is you take 0.1, 0.6, the sum is 0.7. So the new table is going to just give you plus r, L plus r and 1 by 7 and minus L plus r 6 by 7. Okay, so this is what a normalize is. Okay, it's a combination of, it's of course there is an inbuilt eliminate which is happening here, but you don't explicitly do it. You just divide each by the sum. So that's what normalize does. Okay, so that's this operation. So sometimes this is also a useful thing to do. Sometimes but in some queries you might want to also use this operation. Though here in this case, actually, yeah, I mean this was a very different way of doing it. You didn't really have to do a join over R, okay, because R was an evidence. So what you had to do is just join the hidden variables. So let me just write down the algorithm formally. So this is called the variable elimination algorithm to evaluate a query. So I'll just write this algorithm and I will stop after writing this. So variable elimination, so the input is a query like this, P of Q given E1 to EK, okay? And the hidden variables are, let's say, Z1 to Zn. So what you actually just need to do is you have the initial factors. That's we discussed how you write the initial factors, and what you do is as long as while there's a hidden variable left, while there is a hidden variable left, while there is a hidden variable left, uh, what you do is you just do a join over uh, h1. While there's a hidden variable, let us call it h. Okay, so join over h. Okay, so pick some hidden variable and join, or maybe let me just call this hidden variable as the set. Okay, so while there is a set, or let me just write it as while h not empty. Okay, so while h not equal to empty, so h is the set of hidden variables. The set is h. So pick one entry, pick some, let me call it hi from h. One of the hidden variables you pick, you do a join over hi, okay, and that will give you some new set of factors. And then finally you eliminate hi. Okay, you eliminate hi and keep on doing this. Okay, and of course you remove this from h. So h is h minus hi. So you remove this hidden variable from your set and keep doing this. And finally, you might have to do, finally, there might be a join and normalize operation, which you might have to additionally do. Okay, but essentially you do these operations to get the joint distribution. And finally, depending on what your query is, you will have to do a join or normalize. So we will see some examples of this algorithm in the next class. Okay, so I will stop here maybe, and if there are any questions, I'll just hang back. So if not, thanks everyone.